Hi everyone, welcome to the Combinatorics seminar. Today we're very happy to have Alex McDonough from Brown University, and he's going to talk about an intro to chipfiring. And the pre-seminar goes from 3:30 to around 4. Feel free to ask any question. Get away.
Thank you. Yeah, thank you very much. So this pre-seminar, it's not so much like completely required for the main talk. It's more just sort of a side thing that I wasn't able to fit in the main talk, but I think is a really good way to get introduced to it because it's where I started and how I started thinking about chip firing. I have my timely subtitle, How I Learned to Stop Worrying and Love Simplicial Homology, because I learned about homology and never really understood why it was important or what it was all about. And through this project, I actually finally understood what was going on and why, because it just kind of popped into my research. So it was a really fun way to learn about what's going on and all that homology stuff and sort of motivate it. And I'm hoping that other people have that same experience where either you haven't seen homology or aren't too comfortable with it yet, that'll be more understandable, and even gave me an opinion about reduced homology being better than normal homology, which I didn't think would be something I'd have a strong opinion about. So you can look forward to that. This sort of, so feel free to interrupt me if we end up having like a 15-minute interruption so I can like talk with people about some of these things. That's great. And I think we'll learn a lot from it. And it's not vital that I get through everything. And the part about homology that was exciting to me is only kind of halfway through. So feel free to interrupt me every time. Hopefully this will be enjoyable. So let's start. We're gonna fire some chips. So people talk about chips. It's never really clear what type of chips these are. I assume it's like poker chips or something, but I like to think of potato chips because it doesn't make any less sense. So these numbers are the number of potato chips that are on each of the vertices of our graph. And this is a chip configuration when we put the chips on the graph. So what we can do is fire a vertex. So if we want to fire, let's say we want to fire this upper left vertex, then we're going to send one chip to each neighbor. So first of all, it's going to lose 2 chips, and then they're going to move over here and end up on the opposite vertex. So this is what happens after we've fired that vertex. And we could do this again, maybe the bottom left vertex. We'll try firing this. And what we end up with is this chip configuration. We can even fire a vertex a negative number of times. So maybe this bottom right vertex is very hungry and wants some potato chips. So we can pull in chips from neighboring vertices. And one question I'll ask to you, does the order of firings matter? I see head shaking. The answer is it does not. So if you fire one vertex and another, it's the same as going in the opposite order. And it's called the abelian Sandpile model kind of for this reason, because the order doesn't matter. Another question, well, I guess this is the definition first, is that C1 and C2 are firing equivalent if we can reach one from the other by some sequence of firing moves. And some people have restrictions, such as maybe you can't fire something that's already negative, or you can't fire to go negative. I like to just have everything allowed. So firing equivalent if you can get from one to the other by some sequence of firing moves. And by my definition, it's pretty easy to show that this is an equivalence relation, because if you can get from A to B, you can get from B to A by just undoing all of the firings. And similarly, to get from A to B and then B to C, you can just do them one after another and get from A to C. So we have this equivalence relation on chip configurations that we get from these firing moves. And the next question that we naturally want to say is, are there any chip configurations that we definitely can't get to? Any suggestions?
Well, if the total number of chips changes.
Yeah, exactly. So we can't change the total number of chips because all we're doing is passing around some chips. Now, a trickier question, are there other restrictions other than just total number of chips that we have to keep in mind.
Well, that should depend on the graph. Certainly
Yeah.
for some graphs, there wouldn't be any other restrictions.
Yeah, so it depends on the graph.
Well, why can't you just put any number of chips on the configuration to begin with?
So that we can put any number of chips on it, but the question is, starting from one configuration, can we get to every other one by firing chips? So for example, I'd argue for this case, we put some number of chips on the vertices, but just by firing vertices, we can't get to the all zeros configuration. One way that someone pointed out, I didn't even think of this, but someone pointed out another time I gave a similar talk that you can show that the top left and bottom right vertex always, their sum of number of chips has to be either even or odd at all times, because everything is going to impact them both as far as even and odd. And similarly for the bottom left and top right. So one way we can say that this isn't chip or firing equivalent to the all zeros configuration is because we have an odd total number of chips in the top right and bottom left. And again, this is going to depend on which graph we have, but for this particular graph, that's one restriction. Any questions on this so far? Okay. So first of all, since we don't want to have this annoying thing where different numbers of chips are definitely different, we're going to focus on chip configurations that have 0 total chips. And we're going to call these cyclic chip configurations. And this is about the point where people who are familiar with homology are going to start seeing things that are going to scream, this is like topology going on. And we'll get to that soon. But for now, I'm just going to say these are cyclic chip configurations. And now we can define a sandpile group. So the sandpile group of a graph is going to be the group of cyclic chip configurations under pointwise addition modulo the firing equivalence relation. So what does that mean? So I have a little equation here where if we take this first chip configuration and we add this second chip configuration, to get what they equal, we just take every vertex and add the number of chips. But this isn't the only chip configuration that's equal to the sum of these, because this is also equivalent to this one. Can anyone see an easy way to see that this and this are equivalent?
Fire the bottom left?
Yeah, exactly. So if we fire the bottom left, we get from here to here. So these are both in the same equivalence class with respect to this firing relation. But then for the same reason we talked about before, this isn't equivalent to the all zeros configuration. So there's a couple of restrictions. And I do want to mention one thing. I didn't put it in the talk, but it is the most important thing for all the research I do, so I should probably say it, is that the size of this sandpile group is the number of spanning trees of your graph. So that's like the big equation that kind of begins all of the stuff that I've done, and it's based on the Matrix-Tree Theorem. So you'll see more of that in the main talk, but for this I wanted to focus more on looking at this sandpile group and then another type of sandpile group and how we can say that they're actually the same. So there's a million names for the sandpile group, or at least there are 4. Critical group, graph Picard group, graph Jacobian, group of components. And the reason why there's so many names is because this is such an important and natural thing that shows up all over the place. So this has been discovered in completely different contexts. People doing like electrical networks, people doing line bundles of algebraic geometry stuff. It started as like a discrete system talking about self-organized criticality. So this shows up in a lot of different contexts, and people use completely different types of math to talk about this same group. So one thing that I want to focus on is something that I call edge-labeled chip firing, which is how I was able to understand how we can generalize chip firing. And this is a lot of these ideas that I give for the next chunk of the talk is based on work by Backer, Dillaharp, and Nagnabeda. They had a paper a while back talking about like cut lattices and flow lattices, but this is sort of my own personal way that I like to think about these things. So we're going to start with some transportation trucks that are going to move chips from vertex to vertex. We can think of each edge gets some number of trucks going in some direction. So we might have like one truck going this way, 5 trucks going this way, and so on. Now, the thing about these trucks is it's sort of annoying to have to put these arrows onto the graph. So what we're going to do to save us some effort is we're going to actually put a direction on the edges of the graph, and then we're just going to have numbers. So in this case, most of these arrows are matching, so we're going to get positive numbers, but on this bottom one, we have 5 trucks going to the left, but the arrow's going to the right, so we're going to get a -5. And something I want to point out is that this is not a directed graph. It's an oriented graph. And you can do chip firing on directed graphs where you only fire in one direction. That's totally natural, and there's a lot you can say with that. But we're just using the orientation for bookkeeping. And if we change the orientation, like let's say we changed the direction of this arrow, it just changes this to a negative number. And we get the exact same behavior that we get before. So we have to choose an orientation to be able to talk about things nicely, but the orientation that we choose doesn't actually matter. And this is back to normal. So let's come up with some similar terms. So we're going to say that an assignment of an integer to each edge is going to be an edge configuration. So this is some edge configuration here. And we can get a chip configuration from an edge configuration by having each truck take some chips from one place and drop them off at the other place. So for example, can someone tell me how many chips are going to be at this place if we want to associate this with the chip configuration?
Just one?
Just one, yeah. So there's going to be one here because we had one truck going like this. And then what about, I mean, I showed it briefly, but what about here? How many chips do people think are going to be here?
3.
3, yeah, because we're losing 5 chips. Or wait, we're losing -5 chips, and then we're losing 1 chip and 1 chip. So it's going to end up being 3. And this is the configuration that we end up getting. And does anyone notice anything about this chip configuration? I know it's an open-ended question, but
0 total chips.
Yeah, 0 total chips. So this is this is a cyclic chip configuration. I think that's the next bullet point. We're going to call this map from edge configurations to chip configurations partial. This is just the boundary map of a graph, but now we've thought about it in terms of chips, and that's going to be kind of cool. So here's this fact that we realize is that this map is always going to send whatever configuration we start with, it's always going to go to a cyclic chip configuration. And that's because essentially each truck is taking 1 chip and giving 1 chip. So the total number of chips is going to be 0. All right. So now we have our edge labeled chip firing. And we're going to say that 2 edge configurations are edge firing equivalent if their boundaries are firing equivalent. So we can just take the boundary of one, take the boundary of the other, and see if those are firing equivalent chip configurations. And then we can define the edge labeled sandpile group, which this isn't a real thing I've seen anywhere else, but I find it helpful to talk about. This is the group of edge configurations under pointwise addition modulo this edge firing equivalence relation. So I have another example here. If we take this plus this, then we just do pointwise addition. We're going to get this one. And it's a little trickier to see that this and this are equivalent. But the trick that I used is that all of these configurations here, if we take their boundaries, we get the original ones we had from last time. So this is all the same stuff as before. But now we're taking edge configurations and looking at this edge labeled sandpile group. Any questions on this? so far?
Is there a way to like edge fire directly, if that makes sense, like to see what this equivalence does?
That's a great question. So we're going to get to that. Not only is the answer yes, it's actually so nice that it allows us to generalize chip firing beyond graphs. So that's the cool thing about when we're doing this edge firing. But there's two types of edge firing, so we'll get to that too. Any other questions? All right. So now it's topology time. So chip configurations are zero chains. And this group of zero chains is denoted C0. Edge configurations are called one chains. And we have this map, I think it's generally written epsilon, that goes to the total, it starts with a zero chain and it maps to the total number of chips. And then the kernel of this map is the group of cyclic chip configurations, because it's all of the chip configurations that map to zero when you sum their chips. Similarly, we have this map partial that goes from C1 to C0. And we have sort of this pair of maps that we have right here. And we noticed before that the image of this first map is contained in the kernel of the second map. So this is going to start looking really familiar to people who have taken some topology. This group, the kernel of epsilon divided by the image of partial, is the zeroth reduced homology group, and you denote it like this. And yeah, the reason why it's reduced, if we just sent C0 to 0 instead of sending it to Z, then that would be the normal homology group, but that would kind of mess up all the chip firing stuff. So that's why reduced homology is great. How do people feel about this? Hopefully it's a little bit exciting. It was for me, or you already kind of had this understanding, or you weren't as mystified by homology. There's a lot of possibilities. But anyway, now we can ask, how are these two Sandpile groups related? So we know that this normal Sandpile group is some subgroup of the kernel of epsilon. But the other one, if we sort of mess around a little bit, we can say that it's actually a subgroup of the image of partial, and sort of look at what happens after we take that image. And in that case, they both are quotiented out by the same equivalence relation. So that means that these two groups are going to be isomorphic if and only if these two, the kernel of this is the image of this, which is true if and only if this zeroth reduced homology of G is equal to 0. Can anyone tell me when the zeroth reduced homology is equal to 0? Or
Are you looking for a topological condition?
Yeah, sure.
Oh, well, I don't know.
Any conditions people might either remember or know or think is a possibility for this case based on the idea. I mean, you can also ask yourself in the other direction, when should these two groups be the same? And maybe that will help you think of something as well.
My best guess is when the graph is cycle free.
Cycle free is one guess. Any others? The cycle thing is a good thing to point out because there's this idea of there's multiple ways to write the same edge configuration if we are not cycle free, but having two things that are like, if you just add a cycle from one to the other, that's actually the same element. So it doesn't, in sort of a complicated way.
Oh, that would be the first homology
actually
being
need
0.
Yeah, first homology
would
is
be
really
connected,
bad,
right?
Yeah, connected.
Okay.
Connected, exactly. So in general, the zeroth homology is very easy to state compared to some of the other ones. It's just z to k minus 1, where k is the number of connected components. And this means that these two are going to be congruent if and only if G is connected. And in general, you can just, if you want to find the edge labeled Sandpile group, you can just look at each connected component and find the normal Sandpile group of that, which is what people do a lot of the time. If they're working with Sandpile groups, you pretty much assume you have a connected graph. But I thought this was a nice little connection to homology here. The other way you can think about this, if you're wondering like, why should this be true, is that if you take the boundary, not only is the number of chips going to be 0, but the number of chips in each connected component has to be 0. So you can get something that's in the kernel, but not in the image of the other thing, if you put like 1 total chip on one component and -1 total chips on the other one. That's not going to be in the image of this map partial. And now it's time we can play around with this edge labeled Sandpile group, as Kalen suggested, and find if we can say something like chip firing in this context. So we're gonna, we already know this definition that 2 edge configurations are edge firing equivalent if these 2 boundaries are firing equivalent. But let's do a more useful definition. By that I mean, let's do a definition that gives us something new instead of just playing off what we already know. So let's look at this partial. We can write it as a matrix where the rows correspond to the vertices and the columns correspond to the edges. And then we get a -1 and a +1 in each column. And we just switch which one's -1, which one's +1 if they were opposite oriented. So what happens if we fire a vertex? Well, what happens is we're going to do this. So we're subtracting 2 from here and we're adding 1 to each of those, but it sort of looks like this. And if we put that in edge language, we're doing this. So we're going from here, we're adding this or subtracting. Yeah, we're adding this if we're firing B. And something magnificent is this is actually exactly what happens if you add this row of the matrix. So we have 1 for, or subtract this row, I should say. We have 1 for AB because we have -1, we're subtracting 1. And then we have -1 for BC. So when we subtract that, we get +1. And that's exactly what happens when we fire vertex B. So this is how we can find out exactly what's happening about firings just from this matrix. And then, yeah, we subtract some row of this partial matrix when we fire a vertex. But is there anything else we can do? We kind of alluded to this earlier a little bit. How else can we do something without changing the equivalence class other than firing vertices? What can we do now that we couldn't before?
We could just try putting new numbers on the edges, maybe.
Yeah, so we can put new numbers on the edges, but if we want to make sure that we're in the same equivalence class, we don't want to leave our equivalence class. So is there a specific thing we can add to the edges to make it so that we maintain our equivalence class? This is sort of connecting to that idea when we were talking about, oh, I'll let you say your thing.
Oh, I was going to say maybe like add the same number to everything.
The same number to everything, I think, can that work? That's not always going to work, I don't think.
I take that back. Yeah, I don't think that'll work.
You're thinking like linear combinations of the rows?
Well, linear combinations of the rows, yeah. That would be like firing one vertex and then firing another. So if we do like B and then C and then A or something, that's like we fired B and then we fired A and then we fired C. So we can do that, but there's actually a different type of configuration that is going to be edge firing equivalent that doesn't come from some sums of rows. And this kind of goes back to someone was saying that they felt like we needed to be on a cycle-free graph to be able to have edge firing make sense. So what else could we do?
Can you rotate around a cycle?
Yeah, we can rotate around a cycle, or in other words, we can add. So this, we can add some one chain with trivial boundaries. We can add a cycle. So for example, we could add 1 here, 1 here, -1 here, and 1 here, and that boundary is going to be 0. So if we add that, we're not changing the boundary at all. So in particular, we're staying in the same firing equivalence class. And what does this come from? Well, it's actually, if you take these 4 rows or 4 columns that were associated with this, adding this circuit, then we take AB plus BC plus CD minus AD. That's going to give you 0. And that's true exactly because this is a circuit. Some people who have done some more of the graph theory might recognize this as like the way that you categorize when you have circuits. But another way of wording this is that we're adding an element of the kernel over Z of this partial map, whereas adding the firings is going to add the image of the transpose. So we can actually say that 2 edge configurations are edge firing equivalent if their difference is in this sum of the image of partial transpose and the kernel of partial. And I think that's probably a good place to stop because we're running out of time. So I don't know if people have any last minute questions. I can say briefly that the way the rest of it is going is that we did this for this specific matrix here, this like matrix that we got from partial, but we can actually kind of cut off the head and get this matrix that has the same properties. And then just skipping ahead a little bit, what we can do is get this bigger matrix, which you're going to see in the main talk. So it's you'll get to see this again, but the image of this matrix transpose is going to be exactly the same as the ways that you can get from one chip configuration to another. So this is a new way of talking about this firing equivalence on our edge labeled Sandpile group, which we said is basically the same as the normal Sandpile group. And with this perspective, we actually end up not needing to talk about the vertices, which is useful for reasons that I won't get into right now. So this is something we can say as a Sandpile group. Thank you for listening.
All right, let's first thank our speaker. Is there any further questions?
I'm wondering if you know the homology of a space or you know the space, can you find a Sandpile group that's going to go with it?
Yeah, so
I mean, like a graph with a Sandpile group that'll go with it?
All the homology is going to tell you is, how should I say this? So I think that there's a perspective, and this is kind of getting into the, so first of all, I should say there's a way of extending this idea to simplicial complexes and cell complexes, which was Duval, Klivans, and Martin worked on. And that was sort of what I started looking at, that I eventually came up with my own perspective that's more using matrices and matroids than using the ideas of homology. But one way you can word it is that you, so first of all that's good. So yeah, if you're looking at this, I think you have to look at all of the different, okay, here's the right thing. The spanning trees are the maximal things with trivial first homology. of our graph. Because if you have a
Okay.
circuit, then you have non-trivial first homology. And the number of these spanning trees is exactly the size of the Sandpile group. So by counting the number of these maximal things with trivial first homology, then we get what the size of the Sandpile group is. So there's strong connections between the Sandpile group and homology, definitely.
All right, I guess we'll be back at 4:10 for the main seminar. So there's an 8-minute break.